Hello and welcome to Cutting Edge Strain Engineered Solid State Devices. This is the topic of my research and my interest since the past 12 years. So I'm skipping the initial introduction portion, why strain is there, what causes strain, how strain affects and leads the degeneracy of silicon 6 energy values, constant energy values. One most important aspect is that uniaxial strain is far better than biaxial one. And the strain depends on the fabrication process flow, therefore it is referred to as process-induced strain. It again has two parts, process-induced and substrate-induced or global strain. Nanostructures are very small superfine structures, as we all know, as is expected from the name, and the impact of strain on such nanostructures is very much evident, far more than other ordinary structures. So attributes of strain engineering in solid state devices. First, what have I done in my research? Step-by-step process-induced stress due to the sequential process flow relevant for MOSFETs. Development of analytical model capable of considering both process and substrate-induced thermoelastic and lattice mismatch strains. The concept of commercially available or applicable insulator on silicon substrate that enables carrier mobility boosting through stress engineering by varying the fractional insertion of the nanowire into the substrate. Facilitating the symmetric CMOS design, which is a feat that has not been achieved till now, stress engineering in FinFETs, and finally non-equilibrium Green's function application. To find out what is the advantage, what have we gained by using this kind of strain engineering. For ANSYS multiphysics software, we have used finite element method. For calibrating the software, we have calibrated the software with experimental results and our analytical results as well. And this must be clearly borne in mind that the more fine is the mesh of the structure used in our ANSYS simulator, the better are the results. However, increasing the mesh fineness also increases the time of simulation. Therefore, there has to be an optimization between the fineness or coarseness of the mesh and the time of simulation. So this is the basic structure from the we have taken an experimental result and our analytical result and calibrated the software to estimate the amount of strain introduced in a silicon substrate which lies on a sapphire on a sapphire substrate, and that the entire thing is embedded in SiO2. You can see the mesh is not uniform throughout. At points it is coarse, at points it is dense as per the requirements. Mesh need not be uniform. Next, the most important part of the research, that is process-specific strain engineering. It follows in 4 parts for the simple MOSFET device. First, the built strain in the silicon due to the underlying Al2O3. Then, formation of the gate stack, that is SiO2, 1 nanometer thin layer, then TiO2, high-K gate dioxide, then polysilicon. Next, sidewall spacious silicon dioxide, and finally cobalt silicide source strain. We see that initially the amount of strain induced along both x-axis and z-z axis were same, but process-specific strain engineering has separated the two line graphs, and therefore uniaxiality has been achieved. Next, we proceed for designing strain engineered FinFET. It will be very similar to the UTB MOSFET, but the one difference being the fin will be embedded into the substrate, whereas the silicon channel region was just lying atop of the substrate. The matrix can be assumed to be semi-infinite with respect to the small silicon fin, and under such circumstances, with such assumption actually, we have calculated the induced strain analytically, compared that with Silvaco Atlas and with ANSYS multiphysics, and these are the step-by-step integration processes. Same again, first only the fin embedded in the insulator, then 1 nanometer silicon dioxide high-K gate dielectric, then cobalt silicide source drain contacts, sidewall spacious and cobalt silicide source drain contacts. We have tested and we have found that which high-K gate dielectric is the best suited for strain engineering and for which substrate, for hafnium oxide and for Al2O3, We have tested also Al2C, ethylene oxide and TiO2, and we have found TiO2 to be the most suitable high-K dielectric that may be used for this purpose. Next, we have obtained the results using NaGL and Silvaco Atlas, and herein lies the future scope for our research, which I'll be discussing in the next video. Thank you.